The second main point of the last lecture was to explain the Aufbau principle in terms of the extended Bohr model. In the extended Bohr model, Z effective replaces Z. Z effective equals Z minus S. S is the shielding. And the expression for the total energy is now equal to minus RH Z effective squared over N squared. And we can see here then that the Z effective for 2s and 2p are, the energy of 2s and 2p are different, which is what we expect from the Aufbau principle, since 2s fills before 2p, therefore it must be lower in energy. And this in the extended Bohr model is explained by the fact that 2p is higher in energy, and it's higher in energy because it has a smaller Z effective, placing it closer to 0. And this is borne out by measurements. The Z effective for 2p in the second shell is smaller than for 2s. For lithium, the difference is just 0.3. But by the time we get to the end of the second shell, neon, it's a whole unit difference, 2.52 to 3.47. And we explained the difference between the Z effective of 2s and 2p last time using the D function, the distribution function. The idea was that we had, if we were to look at it like this, is that here's the 1s, there's the nucleus is here, and the 1s is a shield. I'm going to move that up. The 1s is a shield. And what's it shielding? It shields the 2s and 2p. Here's the 2p. And there, now I'll draw the 2s. And 2s and 2p are shielded from the nucleus by the 1s. But the difference in energy of the 2s and 2p is caused by paying close attention to the distribution function, and that you see that the 2s actually has its inner node has penetrated. The inner node of the 2s has penetrated 1s. It has gotten through the shield. And therefore, Z effective for 2s, since it has less shielding from the 1s, Z effective for the 2s is a bigger number. That's what's responsible for the energy for 2s being higher in energy. But there is a further consequence which we didn't explore last time, but which we are about to explore, which is how does this play out in the change in the shape of the orbitals? And for that, we're going to have to remember the virial theorem. And the virial theorem tells us that E total is proportional to E potential. And let me just move that all up top. And E potential is proportional to 1 over r, the distance to the nucleus. And so what's happening then is this. E total of 2s is now in magnitude bigger than E total for 2p. Remember that 2p is closer in energy to the origin. And that means that r, so the E total 2s is bigger than 2p, what has happened to the R of 2s versus R of 2p? Put in chat. Well, if E total for 2s is bigger than E total for 2p, then EP for 2s in magnitude is bigger than EP for 2p. And since EP and R are inversely proportional, R2s is smaller than R to 2p because EP and R are inversely proportional. And so we can now draw a new picture. The 2s is now smaller, and therefore I'm going to keep the 1s at the same place. But if the 2s is smaller, that means that the function has shifted downwards. And here I'm going to make it even smaller now. It's closer to the nucleus. While 2p is further, keep that in red, and I'll put that outside. So the consequence of the penetration of the 2s means that the 2s orbital gets a bigger z effective, and it actually shrinks due to the virial theorem and to the potential energy. We can now go back and understand what's happening with neon. Neon had a very big difference between 2s and 2p. And why is that? And it's staring us right in the face in this new diagram. And all we have to do is write down the neon electron configuration. And neon is 1s2, 2s2, 2p6. And in this new picture, can you see that now 2p, here I'll draw it right here. Here's the nucleus. Here's the first shield caused by the 1s. But now the 2s is a shield for the 2p. Because the 2s has shrunk, there's now more shielding on the nucleus. And therefore 2p goes even closer to E equals 0. And therefore Z effective for 2p by the time we get to neon, because there's lots of electrons in 2s and 2p in neon. There's lots of shielding from the 2s to 2p. 2p is getting even further away from the nucleus, and that is actually what's responsible for the very big difference between 2s and 2p in neon. And this is actually going to have a consequence when we get to the bonding of elements like fluorine and oxygen with big 2s and 2p differences versus elements like boron and carbon with small differences.